it is.
Let's begin. So today we're very happy to have Promit Ghosal from UChicago Stats. We'll talk about an entropic selection principle for Monge's optimal transport problem.
Thank you. Thank you for the invitation to talk. It's fantastic to be here in the math department. It's not very far from the stat department. We're here. And I see like some students like teaching like a topic course, and this is actually the time of this course. So I just invited all my students here. Okay, so I'll say in nutshell what I'm going to do, and then I'll unwrap the things as time progresses. So optimal transport problem is a like optimization problem, as you can guess, and we're going to regularize it by adding some entropy. And then like what we try to find out is that if we squeeze out this entropy from this optimization problem, then what would happen? So that's kind of the statement of the problem, but I'll try to formally say that we progress. So Monge's transport problem, this is probably like all of us probably heard about this, but maybe familiar to some extent, but I still kind of state it formally. We can say about it. So this is sort of the formal statement of Monge's transport problem. It was not exactly in the same form, but close to what I'm going to write. It was formulated in the year 1791. So for this, what we need is like domain from a d-dimensional space and to probability measure on this two domain. And we'll just write down another thing which we don't need right now, but we'll need it later, which is that set of all coupling between this probability measure mu and nu. This is basically a set of joint distribution on the space x and y, such that their marginal distribution on the x space equals to mu and the y space equals to mu. And the Monge's problem tried to find out a map, a Borel measurable map from the space x to y, such that this map pushes this measure mu to nu. So what does it mean? It means if I take mu measure of a set which is T inverse of B for some Borel set in the space Y, then that should be equals to nu of B. And that should be true for all Borel sets. So it tries to find a map like this, which minimizes this objective function x minus tx d mu x. And this sometimes called Art's mover distance. Not exactly named by Monge, but later people try to sort of calling it in that name. Now, this was proposed in this year, 1781, but for a long time it was not clear that whether such map exists, and even if it exists, like, is there a unique choice of such map? So I'll try to provide some historical context, and then we'll go to the exact statement of the problem. So, first major breakthrough for this particular problem. So one thing I just wanted to mention here that like this is like a Euclidean norm of x minus dx, but you can replace it by some other cost function, other kind of distances. And for that also, it's a valid optimization problem. And you can ask like same kind of question that can one find a map which minimizes such integral. So that would kind of like create a general problem of optimal transport, and people are looking at this generalization of this optimal transport problem for a long time. Kantorovich made a breakthrough in the year 1949 by reformulating it in a slightly different way. But I'll just, for historical context, try to provide what happened to, or what is the first breakthrough made for this problem. So for this one, the existence of the OT map was done by Sudakov in the year 1979, albeit with a logical gap. So it turns out that he made some assumption, and that assumption could be verifiable for dimension d equals to 2. Okay, but people found some counterexample for dimension greater than or equals to 3. So this was a situation, and then this kind of logical gap pointed out by Ambrosio in 1994. This was fixed by Evans and Congo. They used PDE technique to show this existence, and this happened in 1999. But the work that we closely follow for our purpose is the third one, and this kind of carried out the original dream of Monge in a more systematic way. Happens in 2001, and here they introduced this, or kind of formalized the concept of transport race to construct the solution of this optimal transport problem, construct the map that is kind of needed for this solving this minimization problem. Although like this, all this kind of thing is a good story, but I came from a more applied point of view. So for our case, I was motivated from application of optimal transport in statistics in particular for understanding the data depth. It's turns out to be very useful tools. And computation of optimal transport turns out to be a very challenging problem for us. Although there is this breakthrough I mentioned by Kantorovich, there's still it's a kind of a high complexity kind of algorithm that he proposed. So there is the regularization of this problem that we would be interested in, and we would try to see that how to connect this original problem here with this regularized version. So I'll go to this statement of this regularized version of this problem and try to mention some of this progress in that direction. Note it down here. So first, let me just say that what is this Kantorovich's version of this problem? Formulation, sometimes called relaxation. So this is so instead of asking for a map, so what he did is that he asked to minimize this cost function or integrated cost function over a space of coupling. This space of coupling we defined earlier. This is this phi mu b that we defined. And what made him solve this problem is the existence of this dual formulation of the problem, which tried to find this optimized over some linear function of for this new formulation, it turns out it could be sort of like written down in this alternative way, and it's there is a kind of easier algorithm to solve this. That is like what there is a kind of like the main thing that proposed by Kantorovich is this: you can use linear programming to solve this problem. Solve this.
You have some kind of constraint on phi and c, just besides that they're in L1.
Yes. Oh, sorry. There is this other constraint. Phi is less than equals to. It has to satisfy this constraint. Problem, and if we like try to solve this with mu and nu being discrete measure, and if we are given like endpoint mass for mu and nu, the complexity is for this algorithm would be order of n cubed or order of n data points. But this was actually like a problem to solve, like or kind of try to find the solution in practical application. What sort of like created a lot of hope is this introduction of this entropic optimal transport, and that's sort of like what I'm going to write next. This board. This is sort of like where this optimal transpose started becoming like very influential in a lot of this machine learning application. So Marco Couturi in 2013 sort of reintroduced something like this entropic optimal transport. So reintroduced, I'm saying it for a particular reason. So this was kind of like already in a abstract form formulated by Schrödinger when he was solving his wave equation. And so there, what he's trying to find is that this minimization problem. So it's just kind of taking this same formulation as like Kantorovich, but instead of like just taking this integral of the square of this distance between x and y, he added entropy term, which is this what in statistics we call like tail divergence. So it's defined as like tail divergence between two probability measure P and Q is defined as like expectation of the radon-Nikodym derivative of this log likelihood, expectation of logarithm of radon-Nikodym derivative if P is absolutely continuous with respect to Q and infinity otherwise. And so the reason why he added this here, it was noticed that like there is a very simpler algorithm, much more simpler than the linear programming to solve this optimization problem. It's like a bit surprising at the same time that why there could be a simpler algorithm to solve when you kind of like complicating this optimization problem by adding entropy. So it turns out there is a kind of very well-known algorithm in computer science which could be used to solve this, a sinkhorn algorithm. And complexity for this algorithm is just order of n squared instead of order of n cubed. It improves this runtime quite a lot. And that sort of started kind of a lot of this application of this in machine learning, and is still a kind of a very active field of research. Now, the purpose of introducing this new optimization problem is to kind of approximate the one that we wanted to know by taking this epsilon to be very small. So what we really want to understand is that what is the solution that we get by looking at this regularized optimization problem, how it behaves when epsilon goes to 0. Right? So, and there has been a lot of work along that direction, not for this particular problem that I stated, but if you take, instead of like just the distance between x and y, if you take square distance, there are a lot of like things one can do, and there are just multiple papers came out in last 5-6 years, which sort of like almost solved like this, or gave like to complete understanding of like how this a solution of this problem is related to the solution of this unregularized problem. But when it is just the distance, the things are a bit complicated. And let me just write down exactly what kind of problem for this context we would be interested in looking. So first one is that like as epsilon goes to 0, does this pi epsilon converge anywhere? Or at least can we say that if I take a oral set B in the space x cross y, how does this pi epsilon B would behave? Where does it converge? And secondly, if it converge like to some measure, what would that be? The description of that measure be like? If it converges, let's say pi epsilon converges to some pi star as epsilon goes to 0, is there some description of pi star? Now, the understanding which comes from like the other problem where instead of just the distance, one would take like square distance, this pi star which is coming out of this pi, which will come out of this pi epsilon, supposedly the most diffused coupling of like this between mu and nu, which would minimize the original optimal transport problem. So there are some like kind of application of finding out this most diffuse coupling. And so if you can sort of figure out what is this pi star is, that would be kind of answer to this question.
You didn't mention uniqueness when you, in your little history. You're saying that the solution is pi is not unique. And this is picking out one solution. Is that what you're saying now?
Right.
So when you regularize, you just get this.
So it's not clear initially that like wherever this pi epsilon would be converging, whether this pi star, whether that is a like.
There are two separate questions here. I'm asking the uniqueness question. Is the original linear program problem, does it have a non-unique solution?
Oh, for this, yes. For this,
it's non-unique.
It's non-unique, yes.
At least for the first power constraint, and maybe with the square, it's unique.
Yeah, that's true. Yeah. So maybe let me just mention it. that even the solution of this the Kantorovich problem would be non-unique. Although I'll say one more remark in regards to what exactly Caffarelli, Macon, and Feldman did. So they somehow found a notion of transport map or some unique way of defining the transport map, which they call it as monotone transport map. So in the class of monotone transport map, if you want to find a solution of this Monge problem, then one would get a unique map. But I guess here also I should clarify that because this entropy being added to this cost function, and this integrated cost function, the entropy, since it is strictly convex, the solution of this regularized problem is always unique. So the pi epsilon, which is this solution of this solution of UT problem is always unique. So this is sort of the goal of this talk, to try to understand this question in details. Let me just first write down what can be said about the first question, and which is slightly easier to kind of write out. And this could be done for a much more general class of optimal transport problem. So this is the first question is like this: if let's say I have my X space and I have my Y space here, and for the application, let's say, or for the kind of like the statement of the result that I'm going to state, I'll just take them to be bounded, but it would be also stated for unbounded set as well. So I'll take a set B1 here and B2 here. And for now, let's just take both of them to be the closed set. So the statement that could be written down is that this, if I take pi epsilon, is solution of this entropic Monge problem, entropic optimal transport, Monge's optimal transport problem. And pi epsilon of the set B1 and B2 as epsilon goes to 0, ipsum of this is less than equals to minus one times this. Minus increment of the dxy minus y minus this kx minus psi kx psi ky, where psi kx by here solution dual Kantorovich problem. So basically, like, there is a large deviation statement could be made about this the content of the measure pi epsilon for a set B1 cross B2 coming from this product space X cross Y. There is a limit version of this also like present. So if I take instead of B1, B2 some open set, so this infima is over space of set of points XY belonging to the set B1 plus B2.
What does this subscript K mean?
K means Kantorovich. Because we will see another set of potential later, or sort of like similar looking function later, which will be coming from this entropic problem.
It's the Kantorovich problem for the original, not for the epsilon.
Not for the epsilon. So what does it mean exactly? This description says something like asymptotically how the content would behave, but it does not say like how in the limit what like how this pi epsilon would look like. For instance, if I take like let's say the set of points xy for where like this right hand side is close to 0, I don't get much information about those set of points, and essentially those are the set of points which are like important for our purpose, which I will kind of tell a bit later why we should kind of focus on those set of points. So this is sort of at least some description, and this is proven by not actually looking at this original problem, but exploring some let me just say this is done by Arnton. 2021, and this used something called cyclical invariance property. Property of pi epsilon. So it turns out that like the solution of this entropic optimal transport like has some geometric like property which is encrypted by this cyclical invariance property, and like which is like if you know like for the Monge problem or like general optimal transport problem, there is a similar property called cyclical monotonicity. And by exploring this, one can get a like statement like this, which is not reflective of what exactly happened in the limit, at least gives a sort of a deviation type of like result. So this is sort of like some understanding about the first question. For the second one, we need slightly more structural information about what exactly happened for this Monge problem, original Monge problem. And for that, I will just introduce some of these ideas that Coffarelli, Makan, and Feldman had in their paper. So,
Just say one more time, which sets B1 and B2? It's interesting to have this inequality.
right. So the set of points which would be interesting to kind of like find out the content of would be where this right hand side would be exactly equals to 0 or close to 0, because those are the points which would be the determining the support of optimal transport map or the support of the solution of the Monge problem. So, but this result gives an idea that like if B1 and cross B2 is away from the support of optimal transport, then what would happen? That's an important observation, but that's not like a kind of very kind of useful in understanding what exactly happened in the limit. In the limit, we want this set of points x, y where this thing exactly are close to being 0. And here, I just wanted to mention one thing is that there is this epsilon factor. Even if it is like not exactly 0, close to 0, this epsilon, presence of this epsilon factor kind of kills the information there. Okay, so for the second question, what I would try to sort of introduce is something called this transport rate. And the reason, let me first say, is that like, what are the transport rates? So this would be basically some segments, segments with endpoints. So they may not be like line segments; they're just like could be curve like segments as well. Dimensional space, and with this following property, so that that A would be part of the space X, and B has to be part of the space Y. Secondly, this if I take this psi k of A plus phi k of B, that would be exactly equals to norm of A minus B, where phi k and phi k are solution of dual Kantorovich problem.
Question. Mm-hmm. Is the linear program you've written up there, is that what you're calling the dual Kantorovich problem?
This one.
Cool. So that is the dual.
This is the dual control. And this is called primal. And so, third is maximality. So they should not be contained in any other transport rate. Like if I fix the endpoint, I do not expect it to be contained in any other transport rate. And fourth is like if I take, let's say, Z in the transport rate R, whose endpoints are A and B, then this is also if Z belongs to X, then psi k of Z minus psi k of k equals to normal c minus a. And if z belongs to y, then psi k of b minus phi. Sorry,
Fine, I'm sorry.
phi, right? Yeah. Thank you. So it's not clear initially that one would have existence of transport maps. So what a crux of the work of Caprelli, McCann, and Feldman was to kind of prove that this transport ray, such transport ray exists, and furthermore, like union of all such rays, transport ray, would be let me just call them like index by A and B. A and B are the endpoints of this transport ray. Will be the support of the Kantorovich solution of the Kantorovich coupling or solution of the Kantorovich problem. So phi k is the coupling coming from this primal Kantorovich problem, and that would be supported like on the union of this transport ray. Just to give you an example that like that may kind of like some insight. So suppose that I have two domains which are just this two-dimensional like square, and let's say this is like 0 to 1 square, and this is just 0 to 1 square moved by 5 0. And I take like this is my x, this is my y, and like mu is the uniform measure on x, and nu is the uniform measure on y. And the transport rays are basically just the horizontal lines, just piercing this like the this two squares. And on each of this, whatever this Kantorovich solution coming from this this Kantorovich relaxation of Monge problem would satisfy this property. So in other words, this solution would be supported on this kind of horizontal rays, and this is like would be the set of points like this. If I take a x point here, and if I take a y points here, I would get this exactly this property that phi kx or psi kx plus phi ky exactly equals to this norm of x minus y. So this difference that you sort of see here, which is coming from this large deviation problem, would exactly vanish on this transport ray. So that's why like this large deviation is not informative of what's going on the transport ray, whereas the support of the Monge problem is actually this union of transport rays.
Sorry, perhaps I'm being silly. The support of pi k is something I view as a subset of RD cross RD, whereas the union of the rays are a subset of RD.
Here it does seem, so what you have to do is that you have to sort of like take, so if I call this to be like the one transport ray, right? So then what we do is that we take, restrict this transport ray on the x domain. That would give you one interval. And restrict it on the y domain. That would give you another interval. The cross product of that would be the support that I was talking about. And this is probably a slightly simplified form of what it is. Okay, so now, for the second question, we have to say something around like what's going on for this pi epsilon as like around this like this transport ray as epsilon goes to 0. How exactly this pi epsilon wraps around this transport ray. I'll try to sort of like keep this picture here and state. Try to sort of state the nature of this pi epsilon for this picture, and then we'll try to generalize it for like other domains. So what it turns out is that this pi epsilon on each transport rate as epsilon goes to 0 solves a separate minimization problem. So it would be solution of like a string of variational problems. So pi epsilon would converge to a unique limit. We just call it for now pi opt. And this pi opt would be characterized by a class of variational problem. So for instance, if I take this pi opt and restrict it on the transport rate R, so let me call this the transport rate R. So by restricting pi opt on R means it is exactly like you take these two segments of R from on X domain and Y domain, take the product of those two sets, and that would be equals to argmin of a variational problem, which is divergence of pi, and another measure whose Radon-Nicodim derivative, which is absolutely continuous with respect to mu restricted on R cross mu restricted on R. And this pi would be in the space of coupling of mu restricted on R, mu restricted on R, where this F is equals to 2 pi norm of x minus y to the power 1/2. So I'm stating it this for this example, like which is a two-dimensional example. For d dimension, like there will be some change in this, but it would be very minor. So what it means is that, like in the limit, if you restrict this pi epsilon on each of the transport ray, it would converge to a measure on the transport ray, which would minimize entropy in the class of all coupling between this restricted measure of mu and nu on the transport ray. So in a way, to think about this, like you can think about like so initially we start with this pi epsilon. As epsilon goes to 0, what is going on is that the entropy of this pi epsilon with respect to the product measure is blowing up. So it's kind of like an easy argument to do. But then it's this. Where is exactly this what is this kind of total like are this entropy like sort of like coming from like small micro states, and like it's this each of these micro states are increasing in number, and that sort of results in blowing up this entropy. So it's kind of like the understanding people have. And what this result shows is that like this transport ray are basically this micro states where this entropy like gets like trapped. But then since you have like infinitely many micro states, when you sum them, the total entropy kind of gets blown up.
What is that constant C?
So this constant C is a bit mysterious. So for this example, this is a universal constant. That's a very good question. So C is same for all transport ray R. It certainly depends on what kind of mu and nu that we take. But for like the square example, it does not depend on like this any particular choice of transport ray. If you try to generalize it for other domain, then the C would is going to depend on the particular transport rate that we are focusing on. So basically, where is this C coming from? It's a kind of like the vertical derivative of like this phi and psi k along in the direction orthogonal direction of like this transport ray. Now here for
somehow constant.
yeah, so it turns out like for this it's like constant along on the transport ray. Even like for this example, it does not even depend on which particular transport ray that you're looking at. So it's like microscopically there is kind of no changes as you kind of scan through like the whole transport ray. That's also kind of turns out to be very mysterious to us. What is the kind of geometric reason for doing this? It seems that maybe like what's going on is that like when we kind of zoom in near a transport ray, all the transport ray kind of looks, and then every position looks very like same. Like it's like the information are not shared among the transport ray. So let me see. We have like 5 minutes. Okay, so what I will do is that right, so this is a statement for the square domain. Now, if I want to generalize it for like any other domain, let's say in the dimension, there's only like a very minor thing that I have to change. I have to change sort of like this fxy part. Otherwise, the statement would be same. It just would be like you have to like pick a particular transport ray in the dimensional space. You have to restrict this mu and nu separately on this transport ray. That would be sort of like determining the space of coupling that you'll be looking at for this minimization problem. And the description would be now this pi opt, where this pi epsilon would be converging. If we restrict on that transport ray, this would be solving exactly similar minimization problem. Only difference would be this fxy. So in dimension D, this would be equals to 2 pi norm x minus pi to the power d minus 1 over d and times x. So one thing to notice is here that if I set d equals to 1, this factor is no more there. Actually, this result is like that I'm showing here only valid, or like the way it's been presented here, only valid for d greater than equals to 2. For d equals to 1, the behavior turns out to be much more simpler. You don't have to even like bring in this transport ray. And there are like a previous work where people have like a similar representation for this limiting object. So I just should mention that work. So, so for e equals to 1, pi epsilon converges to pi opt given by a variational problem. And it, on the surface, it actually looks a bit different than what it looks like for d greater than equals to 2, but there is you can still make some correspondence between these two different type of variational problem. And this was done by Di Marino and Lewitt in the year 2017. So this work kind of triggered us to consider this problem, and there are other motivation as well. But like at least what they made clear is that like the techniques that they're using could not be extended for like transport ray from dimension 2 onwards. So one has to kind of come up with a slightly kind of different point of view in dealing with like high dimensional case. So what I will do is in 5 minutes, I'll just kind of like say that how exactly this like turns out to be, like what made us sort of like come to this conclusion. And I'll just like be very sort of brief in saying this. Just erase this. First, I'll just put a lot of things under the rug. At least I'll try to give a broad ideas what is responsible for this. So we have to understand the behavior of pi epsilon. Now, what is the information about pi epsilon that is known to us? It's a solution of this optimization problem. But beyond that, there is a characterization that people use quite often. So it turns out that this pi epsilon, like since it's a solution of this regularized problem, is absolutely continuous with respect to product measure. Not only that, its Radon-Nikodym derivative has a very specific structure. So this here also you see like I wrote down two functions. These are a solution of dual entropic optimal transfer problem. It's as epsilon converges to 0, this will converge to this solution of dual Kantorovich problem. So there is kind of like a relation, right? They're kind of tied together, but in the epsilon goes to 0 limit. But this is sort of a very concrete kind of structure of pi epsilon that is known to us. Now, what's going to happen is that if I let this xy to be close to one of the transport ray, one can do some Taylor expansion of this object. And it turns out that if, let's say, I have a transport ray here, and I have taken a point x here and y here, say if the x has like a component of transport ray and a perpendicular component, y has the same, then this thing Taylor expands to object like this. Just like I Taylor expanded this expression around xr and yr, and taking epsilon to be kind of like small. Now this part is like the second part here only depends on xr and yr. If I want to kind of understand this density around xr and yr, I have to somehow kind of integrate out this perpendicular component. I keep this xr yr fixed as it is, and I have to integrate out these two parts here. Now this is a Gaussian integral, a Gaussian density type term. If I just integrate it, just like this this thing which is sitting here in the denominator acting like a variance of this Gaussian distribution would pop out, and this will kind of like lead to a factor like this. Whereas this part will kind of like looks like if I take a Gaussian integral, this would give me a moment generating function type of term. And that would sort of lead to an object like this. So basically at the end, what kind of boils down to doing is that we have to just do expansion and Gaussian integration in the neighborhood of the transport ray. The picture looks simpler for this two-dimensional case, especially for this box example. When one would take a more general case, the transport ray are not like a line. It could be a curve. So there one has to do a lot of stuff like a change of coordinate to make this Gaussian integration happens, and there are kind of a lot of technicalities, but the basic philosophy stands on this, like doing this kind of local expansion. So I'll stop here and happy to have.
Can I ask you a question about the limit that you obtain? Is that a minimum of the original Kantorovich problem or not?
That would be also a minimum of the origin. So this is actually was a erase the theorem. So the previous theorem that I kind of like stated, which is kind of Larry deviation principle, a sort of corollary or sort of a sub result of that is that like this pi epsilon would converge to one of the minimizers.
Sometimes the KL divergence always goes to zero.
Right, exactly.
I'm not seeing the probability normalization in that density F.
This one?
Yeah. How is it normalized?
Yeah, so this part, which is a reference measure, people call it,
Yeah.
You don't have to make it kind of normalized because you're solving this entropy problem.
Oh, I see, because of the entropy is relative.
Yeah.
You don't have to. I see. So it
even
doesn't
if you
matter.
add
what
normalization,
constant
it
is.
doesn't kind of
I
change
see.
it.
Okay. Like we're just.
It's basically
Whatever.
entropy, yeah.
Yeah.
Correct.
Are there any further questions? Thank the speaker again.